So, a few things we need to cover this week, and I think the textbook changed the order of some of this material between editions. I'll cover it in the material that seems most logical to me, and probably before we talk about the test or the root test, we ought to talk about absolute convergence, because the ratio and the root test both use these concepts. Now, we've learned, what tests have we learned? Okay, we've learned the nth term test. That has no requirements on it, but it also can't show convergence. It can only potentially show divergence. And then we have the integral test and the comparison test and the limit comparison test. And all three of those tests have a restriction. All three of those tests require that the terms of the series be positive. So what if they're not? Well, there are a few tests, a few ways we can deal with negative terms. And negative terms show up when you're using this material to study the sine and the cosine. I mean, not to get too far ahead of ourselves, but this is something that we see in actual application. We're not just complicating things for the heck of it. If we have negative terms, there are a few things we can do. The stuff we're going to talk about this week is based on the notion of absolute convergence, definition, or it's a definition, it's a theorem, it's somewhere between the two. But suppose that you take a series and you throw absolute value symbols around the terms of the series. And suppose with those absolute value symbols, this thing converges. Then the series without absolute value symbols also converges. And the part of this that is a definition is that we give that a special phrase. We say that it converges absolutely. And if something converges absolutely, it converges in the normal way as well. So there are a few things we can say. Let's look at a quick example. So a series that looks like this is called an alternating series, and we're actually going to learn a special way of dealing with this a little later. But for now, let's say we've got -1 to the n over 1 divided by n squared. And you know this let's see, better start with 1. What this negative 1 to the n is doing. Let's see. Is it's making half of these terms negative. Negative 1 to the n is negative when n is odd and positive when n is even. So it's throwing in a negative sign every other term. And we can't deal with this using the integral test or the comparison test or the ratio test would work, but we haven't seen that yet. The limit comparison test was what I was trying to say, because these terms are not all positive, and there are an infinite number of negative terms. Like if there were just 1 negative term or 2 negative terms, we could just cross them out. But there are an infinite number. What we can do, now that we've seen this definition / theorem on the previous frame, is ask, well, what if we put absolute values around them? What if we just got rid of the negative signs? And here's where if we're not sort of used to working with absolute values, it's important that we become used to working with them. Some very important material is going to use this. So the absolute value of a product is the product of the absolute value. So we can break it apart like that. And then what's the absolute value of negative 1 to the n?
1.
It's just 1. Because the absolute value of 1 is 1, the absolute value of negative 1 is also 1. What about the absolute value of 1 over n squared? Okay, let's rephrase that question a little. Is 1 over n squared positive or negative, or does it depend on n?
Depends on, no, it's positive.
It's positive, because n squared's positive, 1's positive, the quotient of positive numbers. And the absolute value of a positive number doesn't do anything, so we can get rid of those. And then 1 over n squared is a convergent P series. So if we put absolute values there, the result converges. And that tells you that the original series also converges. It converges, in fact, absolutely, although at this point we're not quite sure what the difference is between converging absolutely and converging. So we were able to handle this by using the notion of absolute convergence. And this is sadly not a one size fix-all way of dealing with negative numbers. For the moment, we're going to just have to take my word that the series I just put on the board converges. Well, once we get to alternating series, we'll get an actual argument for why this is true. By contrast, if we stick absolute values in here, so n is positive, n is going to infinity. So 1 over n is positive. The absolute values around 1 over n don't do anything. This is once again 1. When you chuck the absolute values in, the result diverges. So the original series does converge. We don't have an argument for that. I'm just telling you it's true. It does not converge absolutely. And since we're talking about series converging absolutely, converging not absolutely, we'd probably better get some idea of what that means. And I'm going to keep this informal. If a series converges absolutely, you can treat it like a finite sum. So, for example, you can rearrange terms, you can group, you can add parentheses in, you can do the stuff that you're used to doing with finite addition. I mentioned in sort of the historical background of this material that, that mathematicians were working with infinite series long before they had any formal definition of convergence or divergence. And you might sort of wonder how could they get away with that? And the answer is that the series they were working with were almost all absolutely convergent series. So the stuff they were naively doing worked. And they only occasionally ran into problems when they were looking at stuff like Grandy's series, which does not converge absolutely. You cannot just throw parentheses into it, but they were trying to do that and getting contradictory results. So this is as formal as we're going to be. We might show you an example or two of this, but this this intuitive idea is good enough. So that's the idea of absolute convergence. And as for why absolute convergence works, I mean, as for why this statement is true, well, you can think of a convergent series as finite and a divergent series as infinite. And like, it's just looking at this example. Let me go to a fresh slide. Two, 4, 9, 16, 25. I mean, here we have some addition and here we have some subtraction versus if we don't have those negative numbers, we only have addition. So, I mean, it's, I hope pretty clear that that first series should be smaller than that second series. Because in this first series, we've got some negative terms and some positive terms, and they're partially canceling each other out. You know, this negative 1/9 is making this 1/4 smaller. Here we don't have any cancellation. This positive 1/9 is making this 1/4 bigger. So this series down here should be bigger. This series up here should be smaller. And now we're basically using the comparison test. I mean, not exactly, but the same intuition as the comparison test. If this bigger series is finite, then the smaller series must also be finite. You cannot have an infinite expression that is smaller than a finite expression. And that's absolute convergence. And we present it now because the next test we're going to look at, and this is kind of the big one, but it's going to have absolute values in it. And the reason for that is that it's really an absolute convergence test. It's telling you whether a series converges absolutely. And this test that I'm referring to it's called the ratio test. And the ratio test is gotten by looking at a ratio. In particular, the ratio test is going to involve looking at ratios that look like that. A sub n plus 1 divided by A sub n. And the ratio test is based on the idea that convergence is really quite difficult. It's quite difficult to add an infinite number of expressions together and wind up with something finite. So because of that difficulty, you know, these expressions for the series to have any chance of converging, these expressions have to be going to zero. And that's not anything new. That's the nth term test. But we also know the harmonic series these terms are going to zero, but the harmonic series diverges. So just going to zero isn't good enough. If we want these terms to be going to zero, or rather, if we want the series to converge, these terms ought to be going to zero fast. And how can we sort of measure that? Well, if we want, for example, a sub 2 to be much smaller than a sub 1, one way of saying that is that the fraction a sub 2 over a sub 1 should be small. You know, 1 is much less than a million, so 1 over a million is small. 99 is not that much less than 100, so 99 over 100 is kind of large, or at least close to 1. 101 is not smaller than 100 at all, so 101 over 100 is also large. So the screen just froze up on me. There we go. The ratio test is based on the idea that for convergence to happen, this fraction ought to be relatively small. And just like the limit comparison test, I mean, you can't really just look at this fraction because n is going to infinity. What's a sub n plus 1 over a sub n? It depends, but you can look at the limit as n goes to infinity. And we don't actually have to be super small. The cutoff here is 1. If the limit is less than 1, the series converges. If it's greater than 1, the series diverges. Sadly, the ratio test has a failure state. If this fraction is approaching 1, we don't get any information. We could have convergence, we could have divergence, we could have absolute convergence, we could have convergence that's not absolute. So this is just a complete failure state. It's not giving us any information. But this is the ratio test. And the ratio test is sort of the default test for a lot of applications. The ratio test works really well with powers, and the ratio test works really well with factorials, and the applications we're going to be most interested in have powers in them, and they have factorials factorials in them. So the ratio test is practically tailor-made to the sort of applications we want. Let's see this in action. And we've already made an argument via the comparison test that 1 over n factorial is a convergent series. Now let's verify that, or let's argue it a second time using the ratio test. And to use the ratio test, we need to have some idea of how factorials work. So as I keep saying, they're going to keep coming up. So a sub n plus 1 over a sub n. And these are all in these big absolute value signs. The absolute values aren't going to end up doing anything in this particular case, but we'll leave them in for now. 1 over n plus 1 factorial, 1 over n factorial. And because 99 times out of 100, the series we're looking at are fractions. When you use the ratio test, it's very typical. You get something like this. You get an improper fraction. You get a fraction of fractions. And we can hopefully deal with this division of fractions. You flip the denominator and you multiply. And we wind up with this. And we're going to have to take a limit at some point. But for now, I just want to look at n factorial over n plus 1 factorial. And I want to make an observation that we're going to use again and again, that when you have a fraction of factorials, you're always going to have heavy cancellation. Because what's n factorial? Well, it's n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And what's n plus 1 factorial? Well, it's n plus 1 times n minus 1 times n minus 2 all the way down to 1. And what you might see here is that n plus 1 factorial is n plus 1 times n factorial. So in the fraction, n factorial over n plus 1 times n factorial. The n factorial on the top, the n factorial down below, these cancel out. N is positive, So n plus 1 is positive. So 1 divided by n plus 1 is positive, and that absolute value isn't doing anything, and we can get rid of it. So the limit as n goes to infinity of this fraction is the limit as n goes to infinity of 1 over n plus 1. And again, very loose notation there, but 1 over infinity is 0. And 0 is less than 1. So the ratio test tells us that we have convergence. It's very important to keep the ratio test and the limit comparison test distinct in your mind, because both of those tests involve taking a limit of a fraction, but you interpret them in totally different ways. If we were doing the limit comparison test, then getting a 0 would be a failure state. To use the limit comparison test, you're looking at a positive finite number. So something that's greater than 0, less than infinity. Using the ratio test, getting 0 isn't anything special. It's a limit that's less than 1. The ratio test says that if the limit's less than 1, we have convergence. So this is not a failure state. Let's complicate things a little. Let's just look at another example or two. Let's look at 2 to the n over n factorial. So this is kind of interesting. It's very hard to look at this, at least I think it's very hard to look at this and have a lot of intuition about what's going to happen. Because for this to converge, this has to be a small fraction, and that 2 to the n, this 2 to the n is really big. Ordinarily, having a 2 to the n in the numerator is more or less going to guarantee that this does not go to 0 and that it diverges by the nth term test. But the n factorial is also really big. The n factorial is trying to make this fraction into 0. So we have these two things that are both getting really big really quickly, and they're fighting each other. And we might not have a lot of intuition about which of them is going to win that fight. The nice thing about the ratio test is that it's completely mechanical. The limit comparison test requires intuition. The comparison test requires intuition, because in both those cases, you've got to decide what you're comparing the thing to. That's something that you have to make up. The ratio test requires no intuition. It's completely mechanical. We'll look at these ratios and we'll take a limit and we'll see what happens. just so that I'm not writing lim n goes to infinity a dozen times, I like to just simplify the ratio first. We'll take a limit at the very end. Two to the n plus one over n plus one factorial divided by 2 to the n over n factorial. We get these very messy improper fractions whenever we use the ratio test. We flip that denominator and then we multiply. That's how we do fraction division. And well, let me just write this. So when we flip this denominator, this n factorial goes up here. This, nope, this 2 to the n, not 2 to the n plus 1, goes down there. When we use the what am I saying? When we use the ratio test, we get these things and we group terms together to do simplification. That is, we have these n factorials, and the n factorials are going to cancel. And we have those 2 to the n's, and those 2 to the n's are going to cancel. So, I mean, this isn't strictly necessary, but it might make the simplifications and cancellations easier if you break this apart like so. So what's 2 to the n plus 1 over 2 to the n?
The same as 2n plus 2 to the 1. So the 2n cancel the 1 at the top.
Yeah, the 2n cancel. So you subtract the powers. N plus 1 minus n, we're just left with the first power. We get 1, 2, and then n factorial over n plus 1 factorial. We did this in a previous example. It's 1 over n plus 1. And once again, these absolute values aren't doing anything because 2 is positive and n plus everything here is positive. We're multiplying and dividing. So the absolute values don't have any negative terms to work on. And now we need to take a limit. The limit as n goes to infinity of a sub n plus 1 over a sub n. We just did a lot of work figuring out what that ratio is. 2 over n plus 1. So that 2 to the power of n really didn't end up doing anything. it threw a 2 into this, but that 2 cannot counteract that infinity. So 0 is less than 1. Again, you're either less than 1 or greater than 1 or equal to 1. And if you're not equal to 1, we get an answer. So this series converges. And in fact, this series converges absolutely. Because this ratio test requires us to take an absolute value, and the absolute value gives us absolute convergence. So that's the start of the ratio test, or rather that is the ratio test, but we should probably look at an example where it gives divergence. We should look at an example or two where it fails. So there's material that remains to be covered. I think we will call this lesson today, though, and I will see you tomorrow.